Welcome to Boring Lectures, a podcast designed to help you fall asleep. We know sleep doesn't always come easily. That's why we're here with content that is deliberately and delightfully dull. Each episode takes a genuinely interesting scientific topic and presents it in the most methodically detailed, soothingly repetitive, and gently monotonous way possible. Our goal is simple: to help you relax and drift off to sleep. Tonight, we'll be taking a methodical tour of the periodic table. We'll explore each element slowly and calmly, without drama or excitement. If you'd like more calm lectures like this, you can follow Boring Lectures in your podcast app, and, when you're not about to fall asleep, leave a rating or review. It quietly helps the show reach others who might need a gentle way to drift off. So go ahead and settle into a comfortable position. Adjust your pillow if you need to. And when you're ready, you can close your eyes or simply soften your gaze. We hope you're bored to sleep. Let us begin our methodical examination of the periodic table of elements by considering its fundamental nature and organization. The periodic table of elements, also known simply as the periodic table, represents one of the most fundamental organizational schemes in all of science. This comprehensive system of chemical classification serves as an icon of chemistry and finds widespread application in physics and numerous other scientific disciplines. The modern periodic table organizes the known chemical elements into rows called periods and columns called groups. Elements in the same group tend to demonstrate similar chemical characteristics. The periodic table remains widely used in educational settings, research laboratories, and industrial applications, appearing on classroom walls, within the covers of chemistry textbooks, and as digital resources accessible through various online platforms and educational institutions. Moving now to the historical development of elemental classification, we shall examine the chronological origins and early systematic attempts to organize the elements. By the year 1700, only a handful of chemical elements had been successfully identified and isolated from various natural sources. However, as scientific methodologies continued to improve and experimental techniques became increasingly sophisticated throughout the 18th and 19th centuries, the rate of elemental discovery accelerated dramatically. Copper, which was known as a pure metal since antiquity, represents one of the elements identified in ancient times, as does lead, both of which were recognized and worked with by early human civilizations thousands of years before the development of modern chemistry. As the number of known elements expanded progressively, chemists and natural philosophers increasingly recognized that some kind of systematic organizational framework might exist to categorize and make sense of these disparate substances according to their properties and behaviors. One of the first systematic attempts to organize elements according to their observable properties came from a German chemist named Johann Wolfgang Döbereiner, who lived from 1780 to 1849. In the year 1829, which marks a pivotal moment in the history of elemental classification, Döbereiner placed various groups of 3 chemical elements into arrangements that became known as triads. These triads represented early attempts to sort elements into some logical order and sets based on their physical and chemical properties. One particularly notable triad that Döbereiner identified consisted of the elements lithium, sodium, and potassium, which are all highly reactive metallic elements that share numerous chemical characteristics. The triads proposed by Döbereiner were based on both physical properties and chemical properties, representing a multifaceted approach to elemental classification. What made Döbereiner's system especially intriguing was his observation that the atomic masses of elements within a particular triad formed a discernible pattern or relationship. Specifically, when Döbereiner examined the triads he had identified, he found that when the atomic masses of the first and third elements in a triad were averaged together mathematically, this calculated average approximated very closely to the atomic mass of the middle element in the triad. Taking the example of the alkali metals lithium, sodium, and potassium, when one adds the atomic mass of lithium, which is 6.941 unified atomic mass units, to the atomic mass of potassium, which is 39.0983 unified atomic mass units, and then divides by 2, the result is approximately 23.02 unified atomic mass units. This calculated value matched remarkably well with the known atomic mass of sodium, which is 22.9898 unified atomic mass units, demonstrating a remarkable numerical relationship between these three elements. By 1829, Döbereiner had identified multiple such groups of three elements whose properties were similarly related, establishing a pattern that seemed to transcend mere coincidence. In addition to the triads of lithium, sodium, and potassium, and chlorine, bromine, and iodine, other triads that Döbereiner recognized included strontium, calcium, and barium as an alkaline earth triad, and another triad consisting of sulfur, selenium, and tellurium. Each of these triads demonstrated the principle that the middle element's atomic mass could be approximated by averaging the atomic masses of the first and third elements, a principle that suggested some underlying organizational logic to the elements themselves. The specific numbers illustrate this principle with clarity. For the alkaline earth metals, calcium has an atomic mass of 40.078 unified atomic mass units. Strontium has an atomic mass of 87.62 unified atomic mass units, and barium has an atomic mass of 137.327 unified atomic mass units, such that the arithmetic mean of calcium and barium is approximately 88.70, which very closely approximates strontium's actual atomic mass. However, despite these promising patterns, the triad system proposed by Döbereiner contained significant limitations that prevented its universal application to all known elements. Döbereiner's system was fundamentally unable to classify or accommodate all of the chemical elements that were known during his lifetime and afterward. Particularly troublesome were elements at the extremes of atomic mass, which simply did not fit neatly into the triadic framework that Döbereiner had proposed. Very low mass elements, such as fluorine, and very high mass elements, did not follow the patterns established by Döbereiner's triads in any consistent or predictable manner. Furthermore, as techniques for measuring and determining atomic masses improved and became increasingly accurate during the mid-19th century, scientists recognized that some of Döbereiner's earlier triad relationships, which had seemed so promising initially, began to fail or lose their mathematical precision when examined more carefully with improved measurements. Following Döbereiner's work, another significant attempt to organize the elements came from an English chemist named John Newlands, who lived from 1838 to 1898. In 1865, and continuing into 1866, Newlands proposed what became known as the Law of Octaves, representing another early attempt to discern patterns in elemental properties. Newlands ordered the elements in increasing order of atomic mass, beginning with hydrogen and proceeding through the known elements of his era, ending with thorium. As he arranged elements according to this ascending sequence of atomic mass, Newlands noticed a striking pattern. Every eighth element, when counted sequentially from any starting point, exhibited similar chemical properties to the first element from which one had begun counting. This observation fascinated Newlands because it reminded him of the repeating pattern of musical octaves, where every eighth note in a musical scale repeats the fundamental note of the scale, just at a different pitch or frequency. The pattern that appeared every 8 elements inspired Newlands to propose a fundamental law of nature, which he called the Law of Octaves. For illustration of Newlands' principle, consider beginning with hydrogen, which is the first element. Counting forward 8 positions through the elements, as Newlands had arranged them by atomic weight, would bring one to fluorine, which does indeed share some similarities with hydrogen in terms of its chemical reactivity and tendency to form certain types of chemical bonds. Similarly, beginning with lithium and counting forward 8 elements would lead to sodium, and these two elements, as had been noted by Döbereiner before Newlands, share remarkable chemical similarities in their extreme reactivity and their tendency to lose a single electron to form positively charged ions. Newlands published his findings in a paper titled On the Law of Octaves, presenting his ideas to the scientific community with considerable enthusiasm and scientific rigor. However, despite the apparent validity of this pattern for the lighter elements, the law of octaves began to fail systematically when applied to heavier elements, particularly those beyond calcium in the periodic table. As additional elements beyond calcium were examined, the octave pattern became less and less precise, eventually failing to predict the chemical properties of heavier elements with any consistency whatsoever. Unfortunately for Newlands, his work was largely ignored by the chemical community of his era and was even subjected to ridicule from certain quarters of the scientific establishment. The reception accorded to Newlands' work within the scientific community was far from enthusiastic, with some prominent chemists dismissing his ideas as too simplistic or merely coincidental, rather than representing any fundamental law of nature. It was not until many years later, decades after Newlands had first published his Law of Octaves, that the pioneering contributions he had made to the development of elemental classification began to receive appropriate scientific recognition and appreciation. By that time, another chemist had already developed a far more comprehensive and ultimately successful system for organizing the elements, a system that would gain international acceptance and form the basis for the modern periodic table used today. Let us now turn our attention to Mendeleev's periodic system, examining his revolutionary innovation and predictive power. The Russian chemist Dmitry Mendeleev, who lived from 1834 to 1907, emerged as the historical figure most commonly credited with the creation and development of the modern periodic table of elements, establishing him as one of the most celebrated figures in the history of chemistry. In the year 1869, specifically in the month of March of that year, Mendeleev delivered a full and comprehensive paper to the Russian Chemical Society that spelled out what would become the most significant aspect of his organizational system. In this paper, Mendeleev articulated the principle that the characteristics of chemical elements recur at periodic intervals as a function of their atomic weight, a principle that became known as the periodic law. This seminal work by Mendeleev represented the first formal iteration of what would come to be known as the periodic law, establishing it as a fundamental principle in chemistry. According to historical records, Mendeleev had embarked on this systematic study of elemental properties while traveling by train, where he began collecting and sorting known properties of elements, almost as though he were playing an intellectual game. He noticed that there were groups of elements that exhibited similar properties, suggesting underlying organizational patterns, but he also noticed that there were plenty of exceptions to these emerging patterns, which suggested that any simple scheme might be insufficient to explain the full complexity of elemental relationships. What distinguished Mendeleev's approach from his predecessors and competitors was his willingness to revise and adjust the experimental data when it conflicted with the patterns he was attempting to establish. Rather than accepting measured values uncritically, Mendeleev sometimes adjusted measured atomic weight values to better fit the patterns his system produced, acting on the assumption that the measured values might contain errors, or that the underlying periodic law was so fundamental that it must be correct even if contemporary measurements seemed to contradict it. Additionally, and even more remarkably, Mendeleev went so far as to predict that certain elements must exist in nature but had not yet been discovered or isolated at the time he formulated his system. When he identified gaps in his periodic arrangement, rather than viewing these gaps as problems or evidence that his system was flawed, Mendeleev made the bold prediction that these gaps would be filled by elements that remained to be discovered. He further predicted the approximate atomic weights and the chemical characteristics of these yet undiscovered elements. This predictive aspect of Mendeleev's work proved to be extraordinarily successful, as his predictions were vindicated repeatedly by the discovery of new elements whose properties matched his predictions remarkably closely. In the 1870s, a series of new element discoveries occurred that fulfilled several of Mendeleev's predictions with striking accuracy, bringing rapidly increasing interest to his periodic system. The discovery of new elements in the 1870s, rather than undermining Mendeleev's work as one might have feared, actually served to dramatically increase the scientific credibility and acceptance of his periodic system within the international chemistry community. Mendeleev's approach to elemental classification differed fundamentally from some of his contemporaries, in that he was concerned with organizing what he termed abstract elements rather than simple substances. This philosophical distinction was significant and profound, as Mendeleev rejected the suggestion that the periodic system implied the existence of any form of primary matter from which all elements were supposedly composed, which was a view held by some chemists and philosophers of his era. Instead, Mendeleev maintained consistently that all elements were strictly individual, indestructible, and irreducible entities, yet he also acknowledged the seeming challenge posed by chemical reactions, in which elements seemingly combined with one another to form compounds. To resolve this philosophical puzzle, Mendeleev drew a crucial distinction between an element in the abstract sense, which he conceived of as an entity that was essentially unobservable but formed the inner essence of physical substances, and the simple body aspect of an element, which could take many different forms depending on circumstances. In the case of carbon, for example, this simple body aspect could manifest as charcoal, as diamond, or as graphite, representing three distinct physical manifestations of the same underlying element. This philosophical clarity on Mendeleev's part led him to the crucial insight that it was the abstract element, characterized by its atomic weight, that was the property that remained constant and unchanged throughout all of the element's chemical combinations and transformations. Mendeleev's genius thus lay in his recognition that just as it was the element in the abstract sense that survived intact during the course of compound formation and chemical reaction, so too the atomic weight was the only quantity that persisted in measurable amounts and could serve as a reliable basis for classification. This profound justification for using atomic weight as the foundation for the classification of elements represented a deeper philosophical understanding than that which had motivated any of his precursors in attempting to organize the periodic table. By associating the abstract element with its measurable atomic weight, Mendeleev had, in a very real sense, given an abstract element a single measurable attribute that would remain unchanged in all of its chemical combinations, providing both a practical basis and a theoretical justification for the periodic system. As we continue our methodical examination, let us now consider the challenges to the periodic system posed by radioactivity, isotopy, and the discovery of the electron. Toward the end of Mendeleev's life, a growing body of evidence began to pose serious challenges to his conception of the fundamental nature of the elements, and thus to the theoretical foundations upon which his periodic system rested. Several revolutionary discoveries in physics during the 1890s and early 20th century revealed that atoms were, in fact, reducible in various ways, and that there existed a sense in which all elements were composed of the same primary matter: protons, neutrons, and electrons. Most alarmingly for the integrity of the periodic system, there was even evidence to suggest that certain elements could be transformed into other elements through the process of radioactivity, which seemed to violate the fundamental assumption that elements were indivisible and immutable entities. The discovery of radioactivity in 1896 seemed poised to destroy the entire periodic system constructed so carefully by Mendeleev and refined by subsequent chemists. This discovery created significant problems for the periodic system because chemists had traditionally considered elements to be substances that could not break down into smaller parts, representing fundamental and indivisible units of matter. If radioactive elements decayed into other substances, as they demonstrably did, how could they still be considered elements in the traditional sense? If they were to be considered elements despite their radioactivity, then how could so many of them fit into the very few gaps that remained in Mendeleev's periodic table, which had seemed largely complete by the early 20th century? Furthermore, as if the threat of transmutation posed by radioactivity were not challenge enough to the periodic system, the discovery of isotopy near the beginning of the 20th century nearly unraveled the entire edifice that Mendeleev had constructed. Isotopy represented the existence of atoms that had identical numbers of protons and thus belonged to the same element by definition, but possessed different numbers of neutrons in their nuclei and thus possessed different atomic masses. Scientists' failure to separate radioactive isotopes by chemical means threatened both the traditional notion of the elements and the utility of atomic weight as a defining characteristic of an element. In 1911, Frederick Soddy, reflecting on this troubled situation in his annual report to the London Chemical Society, wrote the following words expressing his concerns about the foundations of elemental classification. Chemical homogeneity is no longer a guarantee that any supposed element is not a mixture of several different atomic weights, or that any atomic weight is not merely a mean number. This statement captured the deep uncertainty that had arisen regarding the fundamental nature of chemical elements and whether the periodic system could survive the revelations of modern physics regarding atomic structure. However, if the discovery of isotopes threatened to undermine the periodic system fundamentally, the discovery of the electron and the development of sophisticated models of atomic structure provided the key to explaining many of the periodic properties on which the table was based. The crucial breakthrough came when chemists and physicists began to understand that it was not atomic weight, but rather atomic number, the number of protons in the nucleus of an atom, that determined the characteristic properties of an element. The atomic number of an element is defined precisely as the number of protons contained within the nucleus of an atom of that element, and thus serves as a unique and unambiguous identifier of the element itself. Rather miraculously and seemingly against the odds, when scientists reorganized the periodic table to be based on atomic number rather than atomic weight, the arrangement of elements in the periodic table did not change significantly compared to Mendeleev's arrangement based on atomic weight. In fact, organizing the elements by their atomic number rather than their atomic weight resolved many of the anomalies and exceptions that had plagued the periodic system from its inception. Furthermore, understanding how electrons fill the shells orbiting a nucleus, a process described by quantum mechanical principles, explained and provided theoretical justification for the periodic recurrence of properties that formed the foundation of the periodic law. Moving now to examine the modern organization and structure of the periodic table, we shall consider the systematic arrangement of 118 elements. The periodic table as it exists in the modern era contains a total of 118 chemical elements that have been officially identified and named by the International Union of Pure and Applied Chemistry, also known as IUPAC. These 118 elements represent all of the known chemical elements as of the present date, though the possibility of discovering or synthesizing additional elements with even higher atomic numbers remains a subject of ongoing scientific research and investigation. The periodic table arranges these 118 elements into rows called periods and columns called groups, with elements in the same group tending to demonstrate similar chemical characteristics. The table is divided into 4 roughly rectangular areas called blocks, which are designated as the S block, P block, D block, and F block. These 4 blocks represent regions of the periodic table in which the valence electrons, that is to say, the outermost electrons of the atoms that comprise the elements in each block, are filling specific types of electron orbitals or subshells. The S block consists of elements in which the valence electrons are filling the S-type orbitals or subshells. The first 2 rows or periods of the periodic table are labeled the S block because in these 2 rows electrons in the outermost shell are being added to s-type orbitals, with each s orbital capable of holding a maximum of 2 electrons. Elements in the s block include the alkali metals, such as lithium, sodium, potassium, rubidium, cesium, and francium, as well as the alkaline earth metals, such as beryllium, magnesium, calcium, strontium, barium, and radium. Additionally, hydrogen and helium, the 2 lightest elements, are located in the s block, with hydrogen at the beginning of the first period and helium at the end of the first period. The p block encompasses the rightmost 6 columns of the periodic table, consisting of elements in which p-type orbitals are being filled with valence electrons. Each p orbital can hold a maximum of 6 electrons in total, distributed across 3 separate p orbitals that correspond to different orientations in 3-dimensional space, with each individual p orbital capable of holding 2 electrons. The p block contains elements spanning from boron through neon in the second period, and continuing through aluminum, silicon, phosphorus, sulfur, chlorine, and argon in the third period, and so forth, through successively heavier periods. The p block encompasses all of the halogens, which are located in group 17, and which include fluorine, chlorine, bromine, iodine, astatine, and tennessine. The p block also contains all of the noble gases, which are located in group 18, and which include helium, neon, argon, krypton, xenon, radon, and oganesson. Additionally, the p block contains numerous other important elements including carbon, nitrogen, oxygen, sulfur, and many others that are essential for chemistry and biological processes. The d block consists of the middle 10 columns of the periodic table, representing the transition metals and related elements. In the d block, electrons are filling the d-type orbitals of the valence shell, with each d orbital capable in principle of holding 2 electrons, and with 5 d orbitals available in each d subshell, allowing a maximum of 10 electrons to be accommodated in the d orbitals of any given shell. The d block is subdivided into 3 distinct transition series. The first transition series, which consists of the elements scandium through copper. The second transition series, which consists of the elements yttrium through silver. And the third transition series, which includes lanthanum and extends from hafnium through gold. The transition metals exhibit a wide range of variable oxidation states, often showing 2 or more different oxidation states, usually differing by 1 from each other, which distinguishes them markedly from the main group elements. Representative examples of transition metals include iron, cobalt, nickel, copper, zinc, manganese, chromium, titanium, vanadium, and many others that have important industrial and biological roles. The f block encompasses the elements in which f-type orbitals are being filled with electrons and consists primarily of 2 distinct series, the lanthanides and the actinides. Each f subshell can accommodate a maximum of 14 electrons, distributed among 7 f orbitals. The lanthanide series, also referred to as the lanthanoids, and formerly sometimes called the rare earth elements, consists of the elements lanthanum through lutetium, spanning elements with atomic numbers 57 through 71. The actinide series, also called the actinoids, consists of the elements actinium through lawrencium, spanning from atomic number 89 through atomic number 103. The f block elements are often displayed separately from the main body of the periodic table and shown beneath the table as detached series, primarily because if these elements were inserted in their proper positions within the main table based on electron configuration, the periodic table would become extraordinarily long and cumbersome to display, print, and use in practical applications. Let us now examine electron configuration and the periodic law, considering the quantum mechanical foundations that underlie the structure of the periodic table. The shape of the modern periodic table is fundamentally determined by and intimately related to the manner in which electrons fill the various subshells and orbitals as one proceeds through the elements in order of increasing atomic number. The periodic table structure directly mimics the filling of subshells with electrons, meaning that the organization of the table reflects the underlying quantum mechanical reality of how electrons occupy the electron orbitals surrounding the nucleus of an atom. Beginning with the first two elements, hydrogen and helium, their electron configurations are 1s1 and 1s2 respectively, indicating that their valence electrons occupy the first shell and are in the s-type orbital. These two elements are positioned adjacently on the periodic table because they represent the filling of the same s subshell. For the next 6 elements following helium, beginning with boron and continuing through neon, the 2p subshell is being progressively filled with additional electrons. On the right side of the periodic table, specifically in the p block region, these 6 elements from boron through neon are grouped together in columns and rows that reflect the ongoing filling of the 2p subshell. When one moves to the next set of elements, sodium and magnesium, one encounters elements in which the 3s subshell is being filled with electrons. Sodium and magnesium return to the left side of the periodic table, a positioning that parallels their role as the first elements in which the 3s subshell of a new shell is being occupied. Continuing the pattern, the next 6 elements, from aluminum through argon, are filling the 3p subshell, bringing us back to the right side of the periodic table, where the p block elements are located. However, the sequence becomes more complex when considering the filling of d orbitals. Rather than immediately filling the 3d subshell after completing the 3s and 3p subshells, electrons instead go into the 4s subshell, which represents the s orbital of the 4th shell. Only after the 4s subshell has been filled do electrons begin to populate the 3d subshell with additional electrons. This out-of-sequence filling, which occurs because of the relative energies of the various orbitals according to quantum mechanical principles, explains why the transition metals, which have electrons filling d orbitals, appear in the middle section of the periodic table rather than in a different location. The concept of valence electrons is crucial to understanding the periodic table and the chemical properties of elements. Valence electrons are defined as those electrons found in the outermost shell of an atom, that is to say, the highest numbered electron shell that contains electrons. The valence shell is distinguished from the inner shells, which are referred to as core shells, and the electrons within these core shells are called core electrons. The valence electrons largely control and determine the chemistry of an atom, meaning that the chemical properties that an atom exhibits depend primarily upon how many valence electrons it possesses and how these electrons are arranged in the valence shell. Because elements within the same column or group of the periodic table have the same number of valence electrons and the same configuration of valence electrons, the elements within a group exhibit similar chemical properties. For purposes of illustration, consider the elements in the first column of the periodic table: hydrogen, lithium, sodium, potassium, rubidium, and cesium. All of these elements have exactly one electron in their outermost or valence shell, a configuration that can be represented as ns1, where n represents the principal quantum number of the outermost shell, and s indicates that the electron is in an s-type orbital. Because all of these elements possess an identical electron configuration in their valence shells, a single s electron chemists would expect, and in fact observe, that these elements would exhibit similar chemistry, and indeed they do. This group of elements, collectively known as the alkali metals, or group 1 elements, all tend to readily lose their single valence electron to form positively charged cations with a charge of +1, and all exhibit vigorous and often violent reactivity with water and other substances. As we proceed methodically through our examination, let us now turn our attention to periodic trends, examining the systematic variations in elemental properties. Periodic trends are specific patterns that are consistently present within the periodic table, and that illustrate different aspects and characteristics of the various elements, including their size, their electronic properties, and their chemical reactivity. Major periodic trends that are observed in the periodic table include electronegativity, ionization energy, electron affinity, atomic radius, melting point, and metallic character. These periodic trends, which arise directly from the arrangement of the periodic table and from the underlying principles of quantum mechanics and atomic structure, provide chemists with an invaluable and practical tool to quickly predict an element's properties without necessarily having to memorize the specific characteristics of each individual element. These trends exist fundamentally because of the similar atomic structure of the elements within their respective group families or periods, and because of the periodic nature of the elements, meaning that properties recur in a systematic fashion as one progresses through the periodic table. Atomic radius, defined as the average distance between the nucleus and the outermost or valence electrons of an atom, exhibits clear trends across the periodic table. Atomic radius gradually decreases from left to right across a period of elements, proceeding from the leftmost groups to the rightmost groups. This decrease in atomic radius as one moves from left to right within a period occurs because, within any period, all electrons are being added to the same electron shell. Simultaneously, however, protons are being added to the nucleus, making it progressively more positively charged. The effect of the increasing proton number, which attracts electrons more strongly to the nucleus, is greater than the effect of the increasing electron number, which experiences increased electron-electron repulsion. Therefore, as more protons are added to the nucleus attracts the electrons more strongly, pulling the atom's outermost electron shell closer to the nucleus. As a result, the atomic radius decreases as one moves from left to right within a period. In contrast to this trend within periods, atomic radius increases markedly as one moves from top to bottom within a group or column of elements. This increase in atomic radius as one descends a group occurs because electron shielding increases. That is to say, additional electron shells are added below the valence shell, and these inner electrons shield or screen the valence electrons from the attractive force of the nucleus. As the number of electron shells increases, the valence electrons become progressively farther away from the nucleus, and despite the increased number of protons in the nucleus of heavier elements, the net attractive force experienced by the valence electrons decreases. Thus, atomic radius increases steadily as one descends any group in the periodic table, with the smallest atoms in any group located at the top and the largest atoms at the bottom. Ionization energy represents the energy that must be supplied to remove an electron from the valence shell of a gaseous atom of an element. Ionization energies generally increase as one moves from left to right across a period of elements within the periodic table. This increase in ionization energy across a period occurs for a reason closely related to the trend in atomic radius. As one moves left to right within a period, atomic radius decreases, meaning that the valence electrons are held more tightly to the nucleus due to increased effective nuclear charge. Therefore, more energy is required to remove an electron from the atom. Elements on the right side of the periodic table, particularly those with nearly full valence shells, have very high ionization energies because their valence electrons are held very tightly by the nucleus and because atoms strongly resist the removal of electrons that would break their stable electron configuration. Conversely, ionization energy generally decreases as one moves from top to bottom within any group of elements in the periodic table. This decrease in ionization energy down a group occurs because atomic radius increases down a group. As atoms become larger, their valence electrons are farther away from the nucleus and are held less tightly by the attractive force of the nucleus, despite the increased number of protons in the larger atoms. As a result, less energy is required to remove an electron from a larger atom than from a smaller atom of the same element family. The noble gases possess very high ionization energies among all the elements in their respective periods, reflecting the stability of their electron configurations and being directly related to their well-known chemical inertness or non-reactivity. Helium, in particular, has the highest ionization energy of all the elements, consistent with its small size and completely filled first electron shell. Electronegativity represents a measure of the ability of an atom to attract electrons in a chemical bond, or more generally, the tendency of an atom to attract electron density toward itself in a chemical bond. From left to right across a period of elements, electronegativity increases. This increase occurs because, as one moves left to right within a period, atoms become smaller and experience higher effective nuclear charge. Smaller atoms with greater effective nuclear charge hold valence electrons more tightly and thus have greater tendency to attract electrons in chemical bonds. From top to bottom down a group, electronegativity decreases. This decrease down a group occurs because atomic size increases, and the valence electrons become farther from the nucleus and less tightly held, reducing the atom's ability to attract electrons in bonds. The noble gases, as a group, do not have assigned electronegativity values because their outer electron shells are complete and full, making them extremely unreactive and giving them little tendency to participate in chemical bonding in the conventional sense. Additionally, the lanthanides and actinides, due to the complexity of their electronic structure and chemical behavior, do not generally follow simple electronegativity trends and are often excluded from electronegativity discussions. Among the transition metals, although electronegativity values exist and are recognized, there is little variance among the transition metals across any particular period or within any particular group, primarily because their metallic properties affect their ability to attract electrons in the same way that these properties affect the main group elements. Metallic character, defined as the tendency of an atom to lose electrons and behave as a metal, shows clear and systematic trends across the periodic table. Metallic character decreases from left to right across any period of elements. Elements on the left side of the periodic table, particularly the alkali metals and alkaline earth metals, are highly metallic in character, meaning they readily lose electrons and form positively charged cations. As one moves toward the right side of the periodic table, elements become progressively less metallic and eventually transition into non-metallic character, with the non-metals concentrated on the right side of the periodic table. Conversely, metallic character increases from top to bottom within any group of elements. Heavier elements within any group tend to be more metallic in character than their lighter congeners at the top of the group. Let us now examine in detail the major element groups and their characteristics, beginning with Group 1, the alkali metals. The alkali metals, which constitute Group 1 of the periodic table, include lithium, sodium, potassium, rubidium, cesium, and francium. These elements are located in the first column on the left side of the periodic table, and all possess one electron in their valence shell. Alkali metals are among the most reactive metals known to chemistry, and this high degree of reactivity is due in large part to their larger atomic radii and their low ionization energies. Atoms of the alkali metals tend to readily donate their single valence electron in chemical reactions to form ions with a charge of +1, termed the +1 oxidation state. These metals are characterized by their soft texture and silvery color, and additionally, they possess relatively low boiling and melting points compared to most other metallic elements, with the exception that the heavier alkali metals, particularly cesium, have notably low melting points. The alkali metals are less dense than most elements, and in fact, lithium, sodium, and potassium actually float on water because of their low density, representing an unusual property among metallic elements. All of these characteristics exhibited by the alkali metals can be attributed to their large atomic radii and their weak metallic bonding. Because the metallic bonding in the alkali metals is weak, they are easily deformed, which explains their soft texture and their malleability. The alkali metals react violently with water. According to the general chemical equation, M plus H2O yields MOH plus 1/2 H2, where M represents any alkali metal element. The rate of the reaction between water and the alkali metals increases with the increasing atomic weight and thus increasing size of the metal. With the heavier alkali metals, the hydroxides produced are highly soluble, meaning they dissolve readily in the water and are removed from the reacting surface, allowing the reaction to proceed with unabated vigor, potentially resulting in explosive reactions. The reactions between alkali metals and water are highly exothermic, meaning they release substantial quantities of heat. In the case of particularly vigorous reactions, the hydrogen gas that is generated during the reaction can itself react with oxygen in the air, producing additional heat and causing the hydrogen gas to ignite, creating dramatic and sometimes dangerous combustion reactions. Moving now to Group 2, let us consider the alkaline earth metals. The alkaline earth metals constitute Group 2 of the periodic table and include beryllium, magnesium, calcium, strontium, barium, and radium. All elements in Group 2 possess exactly 2 electrons in their valence shells, giving them an oxidation state of +2 when they form compounds. The alkaline earth metals are soft, silver-colored metals that are less metallic in character compared to the Group 1 alkali metals. Although many characteristics are common and relatively consistent throughout the group, the heavier metals, such as calcium, strontium, barium, and radium, are almost as reactive as the Group 1 alkali metals, though they are typically slightly less reactive than their Group 1 counterparts. The alkaline earth metals are highly metallic and are good conductors of electricity. Chemically, they are all strong reducing agents, meaning they readily lose their 2 valence electrons to other substances that are in the process being reduced. The atoms of the alkaline earth metals easily lose electrons to become positive ions or cations with a charge of +2. Most of their typical compounds are therefore ionic in nature, consisting of salts in which the metal occurs as the cation M2+, where M represents any Group 2 atom. Typical alkaline earth compounds include calcium chloride and calcium oxide, which may be contrasted with the corresponding compounds of the alkali metals, which contain M+ ions and have formulas such as sodium chloride and sodium monoxide. The salts of alkaline earth metals are generally colorless, unless they include a colored anion or negatively charged ion. The transition metals occupy the D block of the periodic table and exhibit numerous distinctive properties that set them apart from main group elements. A distinguishing characteristic of transition metals is that they exhibit 2 or more oxidation states in their compounds, usually with oxidation states differing by 1 from each other. This variable oxidation state behavior is in sharp contrast to the main group metals, which typically exhibit only 1 or 2 oxidation states, usually differing by more than 1. In general, transition metals possess high density and high melting and boiling points when compared to main group elements. These high melting and boiling points arise from strong metallic bonding in transition metals, which occurs due to delocalization of electrons, facilitated by the availability of both d electrons and s electrons that can participate in bonding. However, the Group 12 metals, specifically zinc, cadmium, and mercury, represent notable exceptions to this generalization because their full d subshells prevent d-to-d bonding, which tends to differentiate them from the accepted transition metals in terms of their melting and boiling points. Mercury, particularly, has a notably low melting point of -38.83 degrees Celsius and is a liquid at room temperature, representing an extraordinary exception among metallic elements. The ionization energies of transition metals show small changes in their values as one moves across a series of metals from scandium to zinc. This observed small change in ionization energy across a transition metal series is due to the buildup of electrons in the immediately underlying d subshells that effectively shield the s electrons of the outer shell from the attractive force of the nucleus, minimizing the increase in effective nuclear charge from element to element. Let us now examine Group 17, the halogens. The halogens constitute group 17 of the periodic table and include fluorine, chlorine, bromine, iodine, astatine, and tennessine, though some authors exclude tennessine because its chemistry is unknown and is theoretically expected to differ significantly from the other halogens. The halogens are a group in the periodic table consisting of 6 chemically related elements, with fluorine being the lightest and highest in the group, and tennessine being the heaviest and lowest in the group. Fluorine, chlorine, bromine, and iodine are all nonmetallic elements, while astatine and tennessine, the 2 heaviest group 17 members, have chemical properties that have not been conclusively investigated, though tennessine is considered to potentially have metallic character. The halogens show clear trends in chemical bond energy as one moves from top to bottom of the periodic table column, though fluorine shows slight deviation from some of these patterns. Fluorine exhibits the highest bond energy in compounds with other atoms compared to the other halogens, but it paradoxically has very weak bonds within the diatomic F2 molecule itself. This means that as one progresses down group 17 in the periodic table, from fluorine toward iodine and beyond, the reactivity of the halogen elements generally decreases, which occurs because of the increasing size of the atoms as one descends the group. Fluorine is the most reactive of all elements known to chemistry, and it is the only element more electronegative than oxygen. Fluorine attacks materials that are otherwise considered inert, such as glass, and it is capable of forming compounds with the usually inert noble gases, a feat that no other element can accomplish. Finally, let us consider Group 18, the noble gases. The noble gases, historically called the inert gases and sometimes referred to as aerogens, constitute Group 18 of the periodic table and include helium, neon, argon, krypton, xenon, radon, and oganesson. Under standard conditions, the first 6 of these elements are colorless, odorless, monatomic gases with very low chemical reactivity and cryogenic boiling points, meaning they have boiling points far below room temperature. The properties of oganesson, the 7th member of Group 18 and the heaviest known noble gas element, are uncertain because it is a synthetic element that has been created only in extremely small quantities in particle accelerators. The noble gases were characterized relatively late in the history of chemistry compared to other element groups, with the discovery occurring primarily in the latter part of the 19th century and the early part of the 20th century. The noble gases were previously referred to as the inert gases because their filled valence shells, which contain 8 electrons in the case of all noble gases except helium, give them a complete and stable electron configuration that makes them extremely unreactive. Because their filled valence shells give the noble gases complete octets of electrons, following the octet rule formulated by Gilbert N. Lewis in 1916, they are unreactive with other elements and do not require any additional electrons to complete their outer shells, which would be the driving force for most other atoms to form chemical bonds. The first noble gas to be discovered was argon, identified in 1894 by removal of oxygen and nitrogen from air by appropriate chemical reactions. In the 1890s, William Ramsay discovered an entirely new and unpredicted set of elements, the noble gases. After uncovering the first 2, argon and helium, he quickly discovered 3 more elements after using the periodic system to predict their atomic weights. The noble gases had unusual characteristics. They were largely inert and resistant to combining with other substances. But the entire set fit easily into the periodic system that Mendeleev had developed. The noble gases were characterized relatively late compared to other element groups, and their discovery represented one of the first major tests of Mendeleev's periodic law and periodic table. The noble gases have weak interatomic forces between their atoms, and consequently they have very low melting and boiling points compared to most other substances. All noble gases are monatomic gases under standard conditions, meaning they exist as individual atoms rather than as molecules consisting of two or more bonded atoms. The atomic and physical properties of the noble gases show systematic trends going down the group. Atomic mass, boiling point, and atomic radii all increase down a group in the periodic table as one moves toward heavier noble gases. The first ionization energy decreases down a group in the periodic table, with noble gases having the largest ionization energies of all elements in their respective periods, reflecting their chemical inertness. As we approach the conclusion of our methodical examination, let us consider the modern management and evolution of the periodic table. The periodic table as it exists in the modern era is managed and overseen by the International Union of Pure and Applied Chemistry, commonly abbreviated as IUPAC. While much of what is contained within the periodic table is stable and relatively unlikely to change, the IUPAC organization bears the responsibility for deciding what needs to be changed, updated, or revised within the periodic table. IUPAC has created specific and detailed criteria that must be satisfied for the discovery of a new element to be recognized and officially accepted by the international chemistry community. The responsibilities of IUPAC with respect to the periodic table are extensive and multifaceted. IUPAC is directly involved in establishing the criteria for recognizing a new element discovery. IUPAC defines the structure of temporary names and symbols for elements that have been discovered but not yet officially named. IUPAC is responsible for assessing claims regarding element discoveries, resulting in the validation and assignation of element discoveries. IUPAC coordinates the naming of new elements, involving the research laboratory that made the discovery and allowing for public comments on proposed names. IUPAC sets up precise rules for how to name a new element, ensuring consistency and appropriateness in elemental nomenclature. When new elements beyond the originally known elements are discovered or synthesized, they must first be assigned a temporary name and symbol before they can be officially named and recognized as legitimate elements. While an element can have been claimed through the work of a research laboratory, before the claim has been officially validated and before the element is formally named, the element receives a temporary name and symbol based on systematic nomenclature rules established by IUPAC. These temporary names follow a systematic naming convention using numerical roots for the atomic number, resulting in unwieldy names such as ununceptium for element 117, which has since been officially named tennessine, or ununoctium for element 118, which has since been officially named oganesson. On June 8, 2016, IUPAC released the provisional names for the four most recently validated elements 113, 115, 117, and 118. These four elements had been synthesized in laboratories and had been validated as genuinely new elements, completing the seventh row of the periodic table. On November 28, 2016, IUPAC announced the official approved names and symbols for these four elements. Element 113 was officially named nihonium. Element 115 was officially named moscovium. Element 117 was officially named tennessine, and element 118 was officially named oganesson. These additions completed the seventh period of the periodic table, representing a significant milestone in the history of chemistry and elemental discovery. The periodic table of elements represents a magnificent achievement in the history of science, arising from centuries of observation, hypothesis, refinement, and ultimately, the development of quantum mechanical understanding of atomic structure. From the earliest attempts by Döbereiner to organize elements into triads in 1829, through the law of octaves proposed by Newlands in 1865, to Mendeleev's revolutionary periodic system, first published in 1869, the path to the modern periodic table involved numerous contributions from many scientists working across multiple decades and even centuries. Mendeleev's genius lay not merely in observing patterns, but in recognizing that these patterns reflected fundamental truths about the nature of matter, and in having the courage to trust his system, even when faced with contradictory evidence or gaps in knowledge. The modern periodic table, organized by atomic number rather than atomic weight, and understood through the lens of quantum mechanics and electron configuration, provides an organizational framework that has proven remarkably robust and enduring. The periodic table continues to be managed and evolved by IUPAC, which ensures that new discoveries are appropriately validated, named, and integrated into the table. Today, with 118 known elements arranged into periods and groups in the familiar layout taught to millions of chemistry students worldwide, the periodic table remains one of the most recognizable and fundamental tools in all of science. As scientists continue to synthesize even heavier superheavy elements in advanced nuclear facilities, pushing toward ever higher atomic numbers, and exploring the theoretical island of stability predicted to exist at certain combinations of proton and neutron numbers, the periodic table will continue to evolve and expand. Thank you for spending part of your night with this episode of Boring Lectures. If this episode is helping you unwind, you might like to follow the podcast in your app. When you're rested, you can leave a short rating or review if you'd like. For now, just rest. Good night.